Hello, we are talking about power functions and proportionality examples. When we think of power functions, we have the equation y equals c times x to the k power. The k power is a known exponent. And the c value is a positive constant. When we think about proportionality, directly proportional gives us the equation y equals k times x. K is also a constant. So these two concepts overlap. The difference that we see between them is that in directly proportional, we have an unwritten exponent of 1, whereas in a power function, we have a known exponent. The constant k is a different letter, k here, c here, but it's a constant each time, and so the equations are very, very similar. So we'll start reading our example. On wet roads, under certain conditions, the front tires of a car will hydroplane or run along the surface of the water. The critical speed at which hydroplaning occurs is proportional to, and that's the symbol right here for directly proportional. So it is proportional to the square root of the front tire pressure. So let's stop there and look at what we've got. We got a critical speed that is proportional to the square root of the tire pressure. So I'm going to use S for critical speed, and I'm going to use P for pressure. Speed came first, so I'm going to start writing my equation with speed is equal to some constant times, I'm going to use my parentheses there, the pressure. And I have my power in this square root word. So there are two ways that I can do that. I can do the square root of the pressure like that, or because square root is an exponent of 0.5 or 1/2, we could also write this equation as pressure to the 1/2 power. So either one works exactly the same way on the calculator. Most of us think of square root as the symbol rather than the fractional exponent, so I think I'll use this first one. The next sentence then says, given a tire pressure of 20, so I know that that goes inside here, the critical speed is 46.3 miles per hour. And this is that first number that I have in my chart as well. So in order to solve this, I want to figure out what is the square root of 20. So 46.3 equals c times, and that's about 4.472. And then I'll divide on both sides by 4.472. And that gives me c. That constant is about 10.35. So then my formula, the critical speed is equal to 10.35 times the square root of the tire pressure. It says for us to use the equation to complete the chart. And since there's a number of values here, I feel like it's valuable for me to just go to my graphing calculator and let my graphing calculator do this work for me. So here I am at my graphing calculator, and I'm going to go to y equals, and I'm going to type in the formula that we just found. So we have 10.35 times the square root of our variable, which we have to use x on the calculator. And then I need a bunch of values, so I'm going to go set up my table. And I'm going to start my table at 20, because that was that initial tire pressure, and I'm going to have it change by 5s because I was asked for 25, 30, and 35. So we'll go look at our table. And we have our answers here. So 20, we had that 46.3 that was given, and then we have 51.75, 56.69, and 61.23 as our different critical speeds. So let's go write them in our chart. So for 25, we had 51.75, 30, we had 56.69, and 35, we had 61.23. So our last part. In the rain, a car with tires inflated to 35 psi is traveling behind a bus with tires inflated to 60 psi, and both are moving at 65 miles per hour. If they both hit the brakes, what might happen? So let's deal with the car first. Tire pressure is 35 psi. We just looked that up, so critical speed is 61.23. So the car is above critical speed. Which means there's a good chance of hydroplaning. What about 60? Well, we had put all this data in our graphing calculator. Well, not all the data, but the equation. So let's just go look that up. So I have 60 here as my pressure, and that gives me a critical speed of 80.17. So if I continued my pressure, 60, 80.17. So the bus is below critical speed. Which means when it applies the brakes, it will stop. And so this is why, when you learn to drive, we talk about a safe distance behind, so that if the car hydroplanes and slides a little bit, it has room to slow its speed, and it doesn't need to slow much, from 65 down to 61, and then it's below the critical speed, and the tires are most likely going to grip, and it will come to a stop. But it needs that little extra distance because it is actually traveling above the safe speed for the conditions.